Cool. So, hi everybody. My name is Abdullah Joseph, and today we're going to talk about reversing mobile malware. And perfect. So, I work as a security team lead at a company called Adjust in Germany. We do mobile attribution. So, quick summary for that. Usually companies pay us so that they can know which networks bring them the most traffic, advertisement traffic. And we act as the verifier and the attribution provider for those companies. And for that, we actually have our own fraud team. We work closely with the fraud team to protect our company's proprietary SDKs. And that's basically one of the main topics that we are going to discuss today, which is mobile malware, adware to be specific. So, as part of my job is to reverse a lot of malware, especially Android. We see a lot of iOS as well, but there's quite a bit of Android in there. And the agenda, the methodology that we try to use is basically is pretty stable throughout the entire process, and we needed to establish some sort of a methodology that works for us because contrary to what a lot of people think, Windows malware is kind of taking the prime target. Everybody loves Windows malware. All the books are written about Windows malware. Linux malware, there are some. However, most of them are about Windows. Even the tooling for Android malware analysis is mostly open source projects maintained by students. So I'm pretty happy about it. I'm very grateful about it. I try to contribute as much as I can. However, I would like to have some sort of a forum to establish communication so that we can have a good exchange of ideas. And that's why we've created some sort of a methodology with a nice tooling that we like to use, and it's been proven pretty good so far. And for today, we are going to reverse a lovely malware campaign called SimBad, and not named by us, named by Check Point, and see how the analysis process looks like, and then we can talk about the findings. Just as a quick disclaimer, most of the scripts that are used in here are my own scripts. It's written by our team. However, everything is live on GitHub. The link will be provided at the end. And there is a full-length extended write-up for this malware, complete, and on a blog article that I'm going to post at the end. So you guys can go ahead and check it out and even play with the malware sample afterwards yourself. So, let's go. So this is the methodology that we're going to follow. It's pretty abstract and general. That's why you really shouldn't call it too much as a rule book, as more like a guideline. This is the stuff that worked for us. This is the stuff that we try to do. Why do we even have a methodology? Well, because you can try to take the binary and dump it into IDA Pro like a boss, but it's not going to work too many times because, well, you need to know what you're looking for. You need to have a way of telling yourself when to stop and understand that, hey, this technique is working right now. We're doing very good with it. However, maybe right now we should switch to dynamic analysis. Maybe we should run it in a VM and see how it looks like. So that's why having some sort of a step-by-step process helps us think and helps us, most importantly, remember results that happened 2 weeks ago. I mean, we do malware analysis, but we do actually other stuff. So looking at our notes, we need to have a very structured notes so that we can have another member of the team that maybe just recently joined be able to still look at it and make sense of it. So let's talk about it. By the way, the graph is made by Dot visualization language. Beautiful. I just figured out about it actually two months ago. It's amazing. You can do ASCII graphs. Can you believe that? And code. Literally, this is like 3 lines of code. It's beautiful. So, enough about my love for weird terminal command line tools. And this is the SimBad Campaign. This was not too long ago. This was March 2019. And as far as TechCrunch and Checkpoint say, that it affected 200 apps. It was a library that was reported as an advertisement library, as advertisement SDK that you can put in your Android application, and you will be able to, well, at least the Checkpoint write-up that I read, it said that it provides reactive extensions for advertisement SDKs. Reactive extensions, it's one of those new programming paradigms that erupted recently came from .NET, from RX.NET. And it's just a way to include functional programming in your code. It was a fancy new technique that apparently a lot of people loved, and this library was at least saying that it can provide this functionality for your application. And when do we actually, before we start the analysis, we have to talk about this small step, pre-analysis. Why am I even doing this analysis? So there's two ways that you can think about it. There is either innocent until proven guilty or guilty until proven innocent. And on my side, I take the latter, guilty until proven innocent. So I actually assume that the malware is doing something really, really, really bad, and I try to treat it in a virtualized environment. I'm very isolated, and I put every single monitoring tool that I can do before the execution and check the results afterwards. And for me, the most important thing for this entire analysis stage is to understand those two questions. The malware is purported to be able to download APKs, which is the Android package, basically an Android app, and install it on from a C2 server, download it from a C2 server and install it locally without the user's consent. Also, Checkpoint says that the malware is capable of doing something called screen overlays. So screen overlays, I should have actually put a picture in there. It's really beautiful. Now Secure made a very nice write-up about it. Basically, having an image that looks exactly like your home screen, like when Android phone, when you're on your home screen, exactly like it. However, any button that you press will take you, it's a web view. It will take you to a URL. Any button that you press. So in that way, you can have an incentivized advertisement click on a banner without actually the user seeing the banner, without the user even being incentivized to click at the banner. You click on your home screen. You're not clicking on an advertisement. However, a screen overlay will allow the malicious payload to be executed upon a user's click. And this is the claim that that SimBad is capable of doing. And we need to know if that's true or not. So, the analysis stage. First thing, artifact collection. Basically, what is the binary? What is it? What does it have? What linked libraries does it contain? And are those linked libraries in somehow malicious by themselves, or are they third party? We need to know this stuff. Are there any other entry points other than the main entry point? We need to know that. Luckily for us, in Android, all of this information is nicely, beautifully packaged in colors. Well, not colors, this is my Vim screen, but it's packaged in an XML file called androidmanifest.xml. And that's very beautiful because in Windows, there is no such thing as Android Manifest, at least not as far as I know. So everything that the app is allowed to do is packaged into this little file. And basically, you can think about it as a contract between the app and the operating system. This is what I will do in your ecosystem. And this is everything that I have. This is all the activities. This is all the services that I'm able to run. This is all the information that I have from third-party libraries. It's very beautiful. And in here, one of the main things that we found is permissions. So the permissions are what the app is allowed to do in the Android ecosystem. And in here, we found those 7 permissions, 8, that basically allow, in summary, storage access. There's a lot of permissions. There's even a permission for usage of internet. So some of them are pretty mundane, and some of them are very interesting. So, for example, storage access, that's something pretty regular. An app needs to have a way to store data externally. That's not malicious by itself. Collecting device data, it sounds malicious. However, and this is something that our product does as well. Most SDKs, software development kits, most third-party advertisement SDKs collect user data and device data. And I'm not talking about Cambridge Analytica. I'm talking about stuff that are e-privacy compliant, that are vetted by the European Union. It's basically stuff that are not user identifiable, but are needed to identify a device. For example, the Google advertisement identifier. That's something that you can reset immediately, but advertisement SDKs require it. monetization SDKs require it. The third thing is that receive boot completed. This app is capable of having an action. You can think of it as a side entry point, a side door, and it's being triggered as soon as the user boots up his phone. Which is an interesting thing. Like, why would, by the way, this app that we're analyzing, this was a random sample collected from over 200 apps that were infected. But this app is a photo recovery app. So, it's supposed to be like when you, delete a photo, you can watch a video advertisement, and then you press a button and it will, magically recover your photos. I actually did delete some photos from my emulator and it really didn't recover anything. So it's horrible. I left on it 1 star on Google Play. I swear to God. So entry points. This is basically the first point of contact between the app and the operating system. And this is usually launched by the user. So the first one, the main entry point, this is required by Android applications. It's called the launcher. So basically, when you click on the app icon in on your home screen, on your dashboard, basically this is what the piece of code that gets activated. And there are 3 other side entry points. And this is perfectly legal in the Android ecosystem. So one of them is basically called launch-receiver. That's the first side entry point. And it really doesn't have any sort of trigger. There is no broadcast that it's reacting upon. So this is just a question I have for now. Is it internally invoked? Is the main entry point actually calling it? Could be. We'll figure out later. The next thing is UnlockReceiver. This is a very interesting thing in here. User underscore present. It's under action right here. And this is actually when the user has unlocked their phone. Not when the user has opened up their phone from standby mode. When you enter the password and unlocked, this is a system broadcast that gets broadcasted to every app, and any app can react upon it. Why would a photo recovery app want to react upon me after entering my lock screen? It's a good question. And the third one is from com.parse.push. For now, if I didn't do the research, I wouldn't know this, but com.parse.push is, it's called parse backend. It's a reactive backend that is written in Node.js that you can put in your backend. It acts as your backend, and it has a NoSQL key storage database, key value storage database, and it basically has a nice SDK with your Android app so that it can communicate with it. You can have multiple push and pull situations happening in between your app. So now I know that there are one main entry point and 3 side doors. One of them is invoked as soon as the user inputs their password. And this is all readable in an Android.xml, Android manifest.xml file. We still didn't do any of the analysis. We already know quite a bit about the application. And speaking of which, this application wasn't actually written by the developer. Just like any other Android application, just like any other web application as well, most of the code is not really written by the developer. I believe one time I read a statistic by androiddeveloper.blogspot.com that over 60% of an Android application is not actually written by the Android developer. It's third-party libraries. Third-party libraries that do image processing, computer vision, that do database querying, that do something like this reactive extensions, monetization SDKs, advertisement SDKs, attribution SDKs. Most of the app is actually not written by the developer. And this is important because when you do the analysis, you can cut quite a bit of the analysis stage by not having to look at code that was written by the developer. Another important thing is that most of this monetization SDKs are open source. So if you really want to look at it, you can just go onto github.com and take a look at it. And what we found in here is basically those following SDKs, which are simple Google search for the names revealed those websites. So we got Tapjoy, we got Parse, it's the mobile backend. We got AppNext, which is actually a competitor of ours. And we got RxDroider. And this is a little bit weird because I did the research after Checkpoint released their report and communicated it with Google. So RxDroider was already labeled as SimBad malware when I Googled it. So I kind of cheated on that. Like I just Googled RxDroid and it told me, oh, there's the malware. Kind of a cheat because, well, I did the analysis secondhand, but still good. You can still get good results from Google search. And this is just a summary of what we just talked about. The app uses a lot of third-party advertisement SDKs. The app has this weird RxDroider library, and we found that it can collect device data, and it's possibly invocable by a C2 backend. C2 is short for Command and Control Server. It's a name in the malware world, basically a way for a client, usually the mobile in our case, to communicate with a backend service and have commands come in and be able to react upon it. So now we moved through the artifact collection by just analyzing one single file, and we're able to understand quite a bit about the application. We're able to have some keywords that we can Google and we can actually know about it. And now next step is the dynamic analysis. And this is actually really nice step because it's the best thing about it is that if you have a good environment and a good way to tear down and reset, set up that environment again, you can have a lot of nice experiments with it, and you can always try to, poke it from here and see what it does. If I have Google Play installed, how would the malware react? If I remove Google Play, what would happen? You do this theory testing, and then you keep repeating it over and over again. And usually, most of the time, when you repeat it with new variables, you're going to get new outcomes. So this is the environment setup that I had. It's an Android emulator. So Android has this beautiful property that you can run emulators, and it can more or less reproduce the entire code. It reproduce the code if it was not written natively for ARM, because the ARM emulators are a pain in the neck to set up on an x86 host. For ARM, you have to use your test device, so ask your boss to get you a nice Pixel phone to test on. However, for x86 architecture, for anything that is written natively for x86 or for Java bytecode, Dalvik bytecode, it would work tremendously well. There's a couple of scripts in here that I have. This is the teardown step that I talked about. So in here I have one script, installs system level certificates for my transparent proxy. Immediately can see all HTTPS requests without any problems, and it's automated. And in here installs BusyBox because every single emulator, every single API has different Unix commands. So the find that you have, the find command that is in API 18 is not the same find command in API 26. And I'd like to have something stable. That's why BusyBox basically puts all your Unix tooling in any embedded environment that you want, or a mobile device. So, file monitoring, that's very important. So, if anybody worked in the Windows malware world, there's beautiful tool called Rickshot. So, it basically captures registry key values, is the prime way to save key value pairs in Windows, for Windows applications. And Rickshot, what it does is that you can press a button and take a shot, and then do something, activate the malware, do something with the malware, and then press another button to take a second shot, and it's going to show you a delta. And that's a beautiful thing. So with what I wanted to do with Android in here, there is no such tool for Android as far as I know. So you have to roll your own. What I want to do is that I want to take a capture of the file system, because Unix is Android is a Unix system, and Unix, everything is file-based. So I want to take a snapshot of the file system and be able to do something with the malware, activate it, and then take another shot and be able to understand what happened in the middle. So this beautiful tool took like maybe 10 lines of code with Bash. All the scripts are in a GitHub repo afterwards. So if you want to be a nice open source developer and fix it for me and make it in color and everything, please do. And if you find any problems, just report an issue on it. So basically run it once, take a shot, run it again, and you're going to get the diff in this diff.mon file, and basically be able to understand what happened. So dynamic analysis, what we're going to do, network analysis, and we're going to do file monitoring. And this, in here, we ran the malware, and we saw the most important GET request I found was coming from here, at droider.com. and it was giving me this response. It was an empty request, just hitting that endpoint and giving me this response. I don't 100% know exactly what's happening in here, so I'm just gonna put a pin on it and put it to the side and see how it goes. However, Droider.com was associated with RxDroider, and by the way, the website is still live, so the malware authors didn't take it down. And it is running a parse backend. If you go on it, you're going to see the default parse backend dashboard. I know that because I used to work as a software engineer, and we actually use parse for our backend purposes. So as soon as I entered on it, I immediately recognized the parse backend page. Droider.com. So that's from the network monitoring. We had a GET request with a bunch of commands happening, coming from it. In the file monitoring, we saw that these are the files that changed, the ones that are highlighted. However, most of them are actually not related to anything malicious. Most of them are coming from, if you saw the last one here, it's called Fabric. Fabric is a beta testing SDK that the app happens to use. There is another one called Crashlytics. Crashlytics is a crash monitoring SDK that the app happened to use. There's a bunch of them are coming from org.chromium.webview. Those are WebView cookies for advertisements. Most of these stuff are actually not 100% malicious. If I saw something, I don't know, like sys_driver, I'll be a little bit on the lookout, but I didn't really find anything too malicious in here. So with the dynamic analysis, I found the network request, the GET request that I just talked about, and the file monitoring couldn't really show me anything. However, there was a long-running service called overservice, and it was coming from the app. A long-running task, a task in the background running, even if the app is closed and you're navigated to another app, it's still running in the background. That is very legal in the Android ecosystem, and we found that it's running in here. Would be cool to know what it's actually doing. So, we're actually almost at the end in here because the malware, I know it hit 200 apps and it was purported to be pretty big. Java bytecode is very easy to understand. Dalvik bytecode in this case. So it's very easy to actually reverse it and understand how it goes. Each function is very clearly defined. It's not like you're reading ARM instructions obfuscated through a virtual machine. In that case, I highly recommend that you guys see a talk that happened in Hack in the Box by Mr. Alexander Borges, who's standing right there, about deobfuscating virtual machines. So, okay, so static analysis stage. This is what we're doing. We're going to enter one of those doors, one of those main entry points, and we're going to start from there. We have a theory. We have that we think that the app is downloading things from the C2 server and installing it locally. And the other theory is that we know that the app is doing some system overlays. And we have those three doors from before from the artifact collection stage, and we're going to go into one of them, whichever one that you want. The one that I chose is UnlockReceiver. And what UnlockReceiver does is that as soon as you enter your lock screen password and press the enter button and it's accepted, this will run. This piece of code will run immediately, even if the app is not in the foreground. So what this piece of code actually does, I have a small summary on top, and basically as soon as you run it, it's going to launch. It does this small mathematical calculation to determine time. It's like, I think it, as far as I understood, every 60,000 milliseconds, it will launch. It will check that if it has launched within 60,000 seconds, and it will launch again. And it will launch, last line in here, over service, the long-running service that we found in here. And a small analysis in here showed that this actually is the one responsible for screen overlays. I know the code is a little bit complex in here, but basically what it does is that as soon as the GET request has this APK module JSON key, if it exists, it will go down and activate another function, which I'm going to talk about in the next slide. If it doesn't exist, it's going to actually fetch a bunch of app names, and it's going to display it either through market : / or 9apps : // It's going to invoke that URL. What does this URL do? Well, market : / invokes Google Play. So if you right now on your browser, on your Android browser, market : / com.facebook.katana, that's the name of Facebook app on Android. It's going to launch the store page for Facebook in Google Play. 9 apps is the Google Play equivalent for India. It's basically a Google Play. It's an app marketplace that's usually pretty famous in India. And what it does in here is that it fetches the names of packages of apps, and it tries, if you have Google Play, it's going to display it through Google Play. If not, it's going to display it through 9 apps. And it's going to have that screen overlay. As soon as you touch your button on the home dashboard, it's going to go and activate it's going to go to the store page. But why is it doing that? It's basically running a click in the background for a network, for a bunch of networks that are fetched from the C2 server. And it's telling that, hey, you just clicked on an advertisement and got redirected to the store page. I'm going to send a request to an attribution provider to tell them there was just a user that pressed on an advertisement click. And that actually generates money. That generates a lot of money for them. There is something called click per install revenues, CPI revenues. Those make a lot of money. And the idea behind it is that as soon as you're able to press the click in there, possibly you will be able to open one of the installed apps that are installed through here. So the C2 server's second functionality is that it will fetch a bunch of apps, a bunch of APKs, and installs it locally in your device through this piece of code. This piece of code, if you give it in here for the Java devs, java.io.file, if you give it that file into the argument, if you pass it to this function, and you run context.start activity, it will install an APK on your device. So that's it will install an APK on your device with all the permissions of the installer application without your user consent. There is no screen that gets displayed and you press yes on it. So that's something interesting. And we're done with the static analysis stage. I believe I have 2 more minutes. So what we found, launch receiver, door number 1 that we tried was the lucky door. We found everything we need from door number 1. It launches over service. An over service is a long-running thread. Every 60,000 seconds, it's going to make a fetch to the backend C2 server, gets a bunch of application names. Either it will display a store page, or it will install the app locally. That's basically the questions that we had, the 2 questions that we had. And yeah, at this point, you can continue the analysis stage. You can even pen test the server if you'd like. I believe I've written this, I think 10 or 15 days ago. As far as when I checked it, the server was still live. An analyst could contact Google Play right now, just like Checkpoint did. However, for my purposes, we wanted to know the technique of how did this malware do what it's doing. And these are the techniques that are there. And we're done with the analysis. And this, I believe, is my last slide. Conclusions and final thoughts. The idea here was to keep everything on a very much a sane level. I didn't enter any rabbit holes. I didn't go too much into Davlik VM. The RX Droider is actually a pretty big library. However, I only picked 2 functions of it that actually do the entire problem, that do the entire payloads that I'm looking for. We can go into more details in it. However, it depends on the pre-analysis stage, what you're actually trying to achieve with this analysis. So most of one last thing, most of an Android application as well as an iOS application is not actually written by the developer. That saved me a lot of time. I didn't have to reverse SQLite libraries because why would I? It's not something that the developer wrote. That's pretty much it. Here are some references. I believe the material and this slide will be shared in hackinthebox.com, so you will be able to press all the buttons that you want in here. And that's pretty much it. Thank you so very much.
Thank you, Abdullah. It was a nice talk. Looking at the time, we currently do not have any time for new questions. The next speaker is already waiting to enter the stage.
Whoever has any questions, you can just find me outside. So
yeah, he can answer some questions outside. Thank you for your brilliant talk about reversing malware.